Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for coming. We're honored today to have Professor Nigel Shadbolt with us, visiting from the University of Southampton, where he's Professor of Artificial Intelligence in the School of Electronics and Computer Science. He also is a director of the EPSRC, kind of a smallish NSF, but still a large program in interdisciplinary research collaboration in advanced knowledge technologies, which is a fairly large program that's funding some of the ideas you'll be hearing about, hopefully becoming reality someday. Nigel has published several hundred articles on various facets of artificial intelligence. He's written and co-edited 4 books. He's also a fellow and deputy president of the British Computer Society, and he chairs the Society's Knowledge Services Board. I got to know him during his tenure from 2001 to 2004 as editor-in-chief of IEEE Intelligent Systems. I was on the board with him there, the editorial board. He continues on working with IEEE Computer Society's Publications Board as emeritus editor. And today he'll be talking about a topic that's of interest to many people at Microsoft, which is on the potential futures for the Internet. And his talk entitled The Semantic Web, Myth and Reality. So, Nigel.
Thanks very much, Eric. Thank you. Great pleasure to be here. And title like this may not indeed be unique. And in fact, we were speculating on the trouble this whole area gets into, in part, by the title it has, The Semantic Web. I'm going to try and talk a little bit today about how we're understanding that concept, where we think it has got real possibilities for both science, technology and society. Let me give you a little personal history to start with. About 15 years ago, 20 years ago, I was working in what we would now think of as knowledge-intensive applications, expert systems, knowledge-based systems. And the kind of stuff we did in those days is typified by this kind of work, where we were essentially taking a process flow sheet there on the left and trying to elicit from expert chemical engineers enough knowledge, common sense knowledge and engineering knowledge, to realize a 3-dimensional layout of a chemical plant, which we see represented on the right. And that's the kind of work that was very much typical of a certain era of computer science research. Possibly my favorite work in that area was work I did with a brewery to understand how it was that you actually selected your malts to brew beers. A lot of really interesting knowledge acquisition in that project, and it did lead to really a very nice diagnostic support system for the brewers at Eindhoven Brewery in England. And that whole process, that era of work, really did help develop, I think, a number of clear understandings. We came to understand how to represent knowledge and deal with uncertainty. A whole range of methods of uncertainty were developed within this area of work, including Bayesian methods, a variety of uncertainty calculuses. We worked out how to reason with that content, difficult problems about how to acquire the knowledge from experts and from manuals in the domain, and really how to run some of these systems in quite demanding real-time contexts, how to optimize them. But a lot of key challenges, I think many of us working through that era found difficulties in all sorts of areas to do with maintaining the knowledge bases, well-known problem, the knowledge is always changing, what's the currency of the knowledge, how to disseminate the capability. How do we get it out to a very large class of users? How do we reuse hard-won data, content and knowledge? And what I would say about approaches that go under the rubric of the semantic web seems to be changing the way we think about knowledge acquisition, how we think about the knowledge engineering process, and is helping us achieve a degree of interoperability, I think, now and certainly in the future, that really will, I think, be quite impressive. I think it's suggesting a different way in which data, content and knowledge can be deployed. Now, getting behind the myth of the semantic web and some of the overclaiming that goes on is something I'll try and illustrate today, where the advances can be. And this brings me to the project that I've been directly involved with for the past 6 years. Eric alluded to it, the Advanced Knowledge Technologies IRC. That stands for Interdisciplinary Research Collaboration. It's 5 universities in the UK, a UK-funded project on the order of $11 million of funding. And it gave us a 6-year research base to think about the whole issue of integrating a range of services that dealt with knowledge-intensive content in a web context. I mean, the Semantic Web paper was appearing around about the time the project launched in Scientific American and became rather popularized. But it wasn't the mission of this project originally to build the Semantic Web. But we see a lot of what we're doing as discharging some of those ambitions. Okay, let's just give you the kind of 101 intro to the Semantic Web. Many of you may have seen this before, but it's a nice illustration. It's one which says, what does it mean to build a Semantic Web at all? Well, here's a website for a rather attractively placed conference in Hawaii in 2002, the Web Conference. And as you inspect that with your kind of human information processing capability, it's very easy for you to notice things about that website. You can identify the title of the conference. You can identify the URL there in the top left corner. You know that is a page for an event. An event will be expected to have a spatial location, such as a begin time and an end time. Here's a picture of an invited speaker. That's a picture of Tim Berners-Lee, and that tells us that he is a featured speaker in the program. And the point of the Semantic Web is to get hold of content like this and essentially enrich it, add metadata, information about the content itself, to describe some of the relationships and intrinsic properties of those objects. And essentially a lot of work in this area has been about developing standards, varieties of angle-bracketed languages that will allow you to represent core classes and relationships between those classes, so as to represent in a way that machines can begin to understand and interoperate the key content of those web pages. And of course that annotation can extend to anything: databases, scientific structures, workflow, publications, people. And actually Eric Miller has a rather nice talk in which he illustrates some of those opportunities. And I will indeed try to illustrate some of them today. So let's get to the core of one of the ambitions for the Semantic Web, which is this notion of, can we share meanings at a web scale in a significant way so that we can agree on the key terms that we want to use to annotate our data, to agree what it is to be an event or a featured speaker, for example, in the last slide. How do we do that? This is where, again, it's a field, many times in computer science and AI, I seem to have been associated with topics which repurpose terms to the annoyance sometimes of other disciplines. Ontologies here, and the philosophers who originally kind of were using this term in good faith sometimes look at us a bit askance. But in this sense, the way we're using it in our work is to think of it as a shared conceptualization of a domain. Not of everything necessarily, but of an area of interest. It provides a backbone for us to begin to talk about controlled vocabularies, to begin to talk about our content, our databases, our web pages, and so on. And indeed, we've made real progress on that. There's now a W3 World Wide Web Consortium recommended standards for languages to allow us to express the ontologies. And the reason I think we're starting to see some real engagement here is that we can look in domains where significant efforts are now underway to regularize, to look to agree certain core vocabularies, classes of objects and relationships of interest. And indeed, the benefits, of course, communication, interoperability, a degree of control. I'll say something about the philosophical complexities of that in a moment. But if we look at genomics and proteomics, many of the new life sciences are engaged in really large-scale efforts here to take core areas of concern and describe the classes and relationships of interest. In medicine we see it happening. The NIH is a large centre of work in this area. We find it in manufacturing. So for example in the UK we're involved with aerospace manufacturers who want to agree ways of describing objects of interest, whether they be aircraft frames or engines or various aspects of manufacturing itself. And the defense departments, both in the UK and here in the US and elsewhere, are very interested in trying to understand how they describe certain areas of mutual interest. Now, it's worth saying that the effort you have to invest in building an ontology is significant, but even in an area, even the process and act of building an ontology can actually pay dividends. This is some work undertaken at the University of Manchester, where they were actually engaged in building ontologies for proteomics to understand the kind of functional characteristics of proteins. Now, these are large and quite difficult ontologies to construct. Indeed, as well as constructing the ontology, they were using some technology, a description logic and a description logic interpreter, to actually reason over the structures being built, to understand the properties and the relationships, consistencies between these objects. And actually applied in proteomics, the kind of basic problem here is you've got lots and lots of kind of sequence data that describes amino acids. You want to understand something about the function of those sequences. And actually, you can begin to understand the properties of proteins by looking for characteristic motifs. And it's interesting to note that some of the properties that are well described by these sequences now can be described in the ontologies, and the implicit classes implied by those properties can be reasoned over in things like the description logic systems we now have. And actually, in one or two cases, that's led to actual discoveries. So in this domain, there's a couple of examples of some interesting papers where the actual act of classification on this scale, where humans find it quite hard to follow through the implications of the properties that they've assembled, has led to real insights about the actual results and properties of proteins themselves. Okay, so the bad news is that, of course, actually this process of ontology engineering, building these agreed terminologies, is just the kind of challenge it was when we were trying to do knowledge acquisition 20 years ago. They're often highly implicit, they're not often explicitly documented to a level that is often very surprising in areas of engineering and science. These things can admit of real ambiguity or a lack of documentation. They may be ambiguous, vague, inconsistent. And if you're going to actually carry this out on a large community scale for sharing information on the web, then you're going to actually have to model and maintain them, and you're going to have to put in place a social process, which is just as important as the technology process. It's about trying to get groups of like-minded individuals together to try and actually agree how to reduce ambiguity in terms, what the key terms are that need to be expressed, what relationships are important, and so on. They need to be owned, in other words, within organizations. Now, it's worth saying at this point that already some of what I've said can inflame some people's passions. They say this idea of agreeing a simple set of meanings through a description logic, this is just simple-minded. It's worth saying that a lot of what we're doing, appear to be doing in this ontology engineering, would correspond to what in philosophy you can think of as a realist view of meaning. And this goes back, has a long tradition in philosophy. People like Aristotle, Leibniz, Wittgenstein, these people thought it was an appropriate way of thinking about the meaning of terms as those terms picturing the world. And that kind of picture model of meaning stood for some time. Indeed, in the early 20th century, it was seen as promising a language for science. If we could just sit down and actually get a logical characterization of language, all these kind of difficulties in philosophy just disappear. The opposite approach, so-called constructivism, has a much different view, and says there's no simple mapping between our words and objects in the world. We construct objects and their attributes. This is by a complex process of perception and our interests, our culture. And people like Husserl, Heidegger, and indeed Wittgenstein in his later work came to kind of chuck out all of his earlier view of the world as expressing meaning as logic.
Is that a bad sign? Later Wittgenstein, earlier Wittgenstein?
It shows a genius at work, in fact, because both positions were very compelling when argued, and indeed still have their modern adherents. But I think the view here was that he, and Wittgenstein in particular, came to this notion that languages could almost be seen as games or complex procedures, contextualized functions in the world. Now, the interesting game we're at here is that as we build systems that are capable of shifting large amounts of content between themselves, our machines often operating essentially operating task in semantics, having to have a denotational model of what objects in the programming languages mean, you actually start to get this interesting play between two views of meaning. I think that as we actually build systems that are capable of carrying significant amounts of represented meaning, intended meaning, you're getting into a situation also that's a bit like what happened in chemistry and physics a couple of hundred years ago. We're starting to operationalize hard philosophical problems. And as I'll try and go on to say, I don't think this solves our problems about the essential nature of meaning, but I think we can actually see both of those stances at work. And I'll try and show you an example where, assuming we can build these agreed ontologies, which would look a bit like a logical positivist approach, when we see them at work, we realize that in building them, we're appealing to all sorts of complex cultural context settings to understand how the words are worked, to make sure they actually carry on meaning what they did mean. Of course, meaning can change and evolve. So there's a very nice example here of another area where our computation is starting to take philosophical problems and make them a concrete problem to be dealt with. It's rather interesting. So with that little digression, let's get back to some examples of what we can do once we've built or undertaken to think about this ontological view of the world. Now, here's a very simple example. Yeah.
Before you go to philosophy, it is interesting that I think you can map the semantic, the various sides of the semantic web debate, which you'll call that a conversation, to the realist versus constructivist. It's very interesting how that maps onto it.
Yeah, I think it is, actually.
Isomorphically.
Yes, I think it is, and I think there's a lot to kind of unpick there, and I think hopefully we'll come back to it a little bit later in my talk, because I think that is it can draw some of the heat that you can get in this conversation, saying, well, you simply can't sustain a view that is only locked in one view of meaning.
Oh, in earlier, about 3 slides back, he was talking, not to mention the deep philosophy here, constructivism versus realism, and that debate is not necessarily over. But if you look at people that have a lot of trouble with these notions of a big, huge semantic web, and versus the kind of people that are more interested in kind of web services and making that cap smart and designing new things, and it changes with the application, and there is no big semantic web. It maps onto that debate very nicely, those two sides of the kind of argument.
Yeah. And I think it's actually quite important that both views are understood and seen to be at play. It isn't, our machines don't have this deep constructivist view of meaning. They are Tarskian ultimately, but our use of symbols and interpretation of symbols on them is much more complex. Yeah.
Yeah. One of the questions I had relating to what you said, and I'm sorry if you addressed it right at the beginning, I came a bit later. One of your slides about observations, I could have used that slide 15 years ago talking about expert systems. Okay, you could, people have been working in, knowledge representation in AI for a long time, and we seem to be constantly reaching out for things and then rejecting them 10 years later. And expert systems is almost a bad word today. So Bob Kowalski was running around saying logics are going to save the world, and with good intentions, because and then there are bunches of people who've done semantic networks, which to me are sort of semantic webs in another.
Yeah, well, and indeed, as we're going to see, the RDF graphs we build are just like they're just semantic networks in a sense.
Why is semantic web any different?
It's not any different. I mean, the point I want to make is that the problems we're engaging here are very self-similar to problems that the knowledge-intensive systems community, knowledge-based system community confronted. That doesn't mean they all failed and it was a bad idea. A lot of those systems are deployed, used in lots of various contexts. The debate's moved on, though. The research has moved on now to say, if we try to do some of the same things we were trying to do, represent content on a web scale, what would that actually do to the project? Where do the difficult scientific and engineering problems come? Can we solve them this way at all? I think those are just the same questions.
The other question that I have is, are we just renaming things? Is it the same process that we're...
Well, let's get into it a little more and come to a judgment of that. I think there is some renaming, but I think there's genuinely, in this area, a new dimension being brought to the arguments, in the same way that it was certainly the case in 15 years ago in expert systems, knowledge-based systems work, that there was a lot of interest in statistical and approximate methods to actually support reasoning, and that enriched and moved that kind of whole area on too. This is a simple example of an ontology-mediated approach, which I think shows where you can win quickly and easily in a computer engineering context. This is a classic problem taken from the UK. It's the research councils that fund our work in universities. We have a variety of them. Engineering and physical sciences fund physics, chemistry, biology, physics, chemistry and other areas. The Biological Behavioural Sciences Research Council and the Medical Research Council down there, they all have project databases that describe the work they fund, who they're funding, the publications produced and so on. Those databases do not talk to one another. They've been working for 6 years on a common data interchange format and failing to agree on one. It's difficult because actually they're being asked questions now by policymakers and other individuals that say, what is happening on the boundary of discipline? So they absolutely precisely must ask these sorts of questions. So from a business intelligence point of view, you'd like to link this stuff together. A piece of work that I was very pleased about was when our project got invited back into the council that was funding us to try and do a piece of paid work to try and solve this problem for them. And the approach was essentially to decide upon a core set of terms and relationships from the various research councils that they wanted to know answers about. The key things like the grant holders, the grant names, the durations, the co-workers, the institutions involved, the amounts of funding and so on. And essentially built a set of harvesters over those databases and re-represented the core content we were after in our ontology in this RDF data storage system. We call it a triple store. I'll talk about that a little bit more later on. And we built application layers on top of this. The point was the speed of this. It took us about 3 months to build the system. And what that allowed us then to do, and essentially the ontology on the right there is simply describing objects of interest, the fact that you're going to have a time interval that relates to a grant, it'll have a start time and end time. That will map into certain data base formats in particular ways depending on how individual councils have chosen to do it. So there is a point in this system with the current state of the art, you have to write those scripts to get into those data sets at the moment. Oh, happy world when they all agree to expose that data according to a shared ontology. But that's not where they are at the moment, so we built the gatherers. And essentially then we build visualizers on top. That visualizer in this case, very simple, a screenshot of this system. We're looking at an individual here called Beasley and Hurst. Hurst is funded, this is 2000, and we begin to see as we roll through time, over time, in 2001 now, that individual being funded from different research councils with different collaborators. This is essentially the RDF graph that is the intersection of the mapped elements of all of those other databases we were looking at. So this is very straightforward use of a piece of...
By the way to get funding from these agencies, but I probably don't their problem.
Exactly. That was a bit in our mind, I have to say. And this is a browser on our triple store, and you can actually see this guy's quite interesting just because he does derive funding from a variety of research councils. He's one of these connectors, these hubs essentially across disciplines, and we can see how his funding is changing over time. And that's just to show that with a lightweight ontology, a degree of interoperability rapidly follows from this kind of approach. As I say, in an ideal world, we wouldn't be having to write all of these separate gatherers. We would come up with a cross-council agreed ontological fragment, and they would simply expose their data based on that set of RDF standards, you might like to think. Okay. Okay.
I'm wondering if I should save my questions till the end.
Yeah, let me make a bit more progress on the slides and we'll see a few more examples. That's a simple example, I would argue. A more complicated example was one that we built, actually, again, a piece of competitive intelligence for ourselves in the UK. We didn't know whether we could do this, but we were interested to ask ourselves whether we could find out who was doing what, where, with what impact in computer science in the UK. And this is a largish, but not very large domain, 100 or so departments. Lots of different information sources, the databases we looked at earlier, the departmental web pages, the electronic publication databases. We can get to, and indeed in the UK we have to go through a research assessment exercise every 5 years, 6 years, where we submit our best 4 publications and that gets ranked and we decide how much funding we get and so on. So this heterogeneous set of information sets, again we built an ontology to describe the limited world of the academic. And I have to say, it revolves around papers and publications and conferences and PhD students and those sorts of concepts. And then were built harvesters against the various information sets we were interested in. And essentially the application we see here, on the left we see a hierarchy of research areas. That comes from the ACM's description of research areas in computer science. That actually raises an interesting question. There are a number of taxonomies that describe computer science research, and one of the sets of enabling technologies we do have to build are taxonomy to taxonomy mappers, so that we can actually recast one taxonomy in terms of another. And there's some quite interesting work on that, some of it based on information flow theory that shows how we can do those sorts of mappings efficiently. And here we're going to see what we're going to look at the UK, and we're looking at research areas now, and we're going to select a. We can see that there's a little, our area of interest at the moment is over Cambridge, and it's basically acting as a little yellow pages system now, showing us the information the system has represented in its RDF triple store from these different resources about working computer science in that area. I'm now actually placing an area of interest, a lens across this part of the UK, and I'm going to focus in on one area of computer science research, artificial intelligence. It's going to pull back information on the top 5 researchers by grant total. This is where your researchers know how to make you happy, because they found at least one measure where I came out top. And there we have the individuals ranked. And what's actually happening here that's interesting is in the background it's actually pulled out not just the information about me, my papers and areas of research, but it's also computing my community of interest. So here in the bottom right-hand corner we see the COP, or community of interest, and that is the system's current view of the individuals in computer science that are most closely related, associated with. So this is using, again, a simple sort of intersection search over that RDF graph, over that semantic graph of relationships. We have determined which of the relationships should be kind of factored into this community of practice. We've got a tool that I'll quickly show you later that allows us to alter and vary which RDF relationships are taken to be serious. And it's shown me a current view as to my community of practice. Now, this system was gathering data on computer science in the UK on a 24/7 basis. So it was changing over time. It was changing over time. The other thing to note about this is that, again, as we move around the country, one of the things that's important in applications like this is that it has face validity. So it is certainly important that if, as you take this talk around the UK, that people can recognise their community of interest as legitimate, and it's quite good when people can begin to see that this approach has got face validity. Now, again, one of the things that we would be hoping is that rather than us having to harvest all of this kind of pool model of data collection, a view of what we might think of a semantic web that is more interesting is, again, where there is a small core ontology that describes research in universities and the objects of interest therein, and the departments themselves are exposing relevant content against that format. So it becomes very much more a push model. And that is something that in the UK is receiving a lot of interest at the moment, partly because we are engaged on various kinds of metric-based assessment, citation rates, numbers of papers published. People are wondering how you might instrument the various information resources to answer those sorts of questions. Okay. Now, actually, I have talked about standards a little bit. Somebody said, you shouldn't really come, this is where, you shouldn't come to Microsoft and talk about standards, because there's clearly well and deeply held views as to what might and might not work in this area. But it is important to say, I think, that standards in this area are fundamental. The W3C supports standards, and you'll have seen this stack in the past. It evolves and changes over time. And one interesting observation about this is that in some respects, some people's views about exposing information out there in the maximally reusable way is you go as low down the stack as you can get away with, in a certain sense. So that RDF gives us a minimal representation language for representing relationships between objects, and And the higher level layers, things like the ontology, the description logic embodied in OWL, give you more capability. The variants of OWL you can get perhaps are difficult to use in some cases. It's not always clear that the effort you derive necessarily maps to what you want in your domain. If you're interested in doing auto-classification, you might want to go that far. One of the arguments here is that, well, why can't you do a lot of what the semantic web is trying to achieve in XML? You can, okay, fundamentally, but actually it can be quite prolix way of doing things. It becomes somewhat difficult. It's an issue about transparency, expressive utility. The RDF argument is that where you are more concerned about structure and less concerned about the subtleties of serial order, then RDF tends to become a more natural choice. And often in the semantic web what we're interested in are database structures, information about patients in medical domains, for example, rather than the sequence, the precise sequence of a set of statements. And indeed, if you go out there on the web, you can find a whole variety of strongly held opinions about which level in the stack is the right one to be working at. Some people say that the problem with the XML is that you have to do a lot of agreement up front about those formats before you can really interchange. And RDF gives you a slightly freer approach to this, that you don't actually have to agree ahead of loading down the ontology definitions exactly what those terms mean. And I think there's a nice sane voice down there at the bottom which says the semantic web is not an all or nothing proposition. Actually, it's a way, there's a range of technologies here, RDF, friend of a friend, RSS, OWL, and so on, which are all about trying to control the characterization of content and meaning and expose data for reuse. Okay, we can revisit that if people feel that's something they want to really drill down onto. Let me show you the kinds of work we've been doing where once we've got the ontologies built, once we've got the ability to actually annotate content, we can then thread content together and build other sorts of services on top. And I think of this as trying to build information spaces, and often cases that's in terms of trying to understand an overall situation in terms of supporting decision making. One nice example here that we've been working on, this was supported actually by a grant from the eScience, UK eScience program that Tony Hay used to manage a large part of in the UK. This was work on trying to support medical decision making in the area of symptomatic breast disease. In the real world, in real applications, you of course realize that medical practitioners, along with a lot of other scientists, don't have one ontology. There are multiple viewpoints. And how do you represent those and how do you map between them? So in breast disease, you will get an expert on digital X-ray and an expert on the MRI images and an expert on ultrasound, and they are not the same people. Of course, those instruments show the world in different ways. The objects that are viewed and the relationships between them are quite different. The oncologist will have a different way of thinking about the world, the histopathologist another. And so actually here the trick is to understand what elements of their representations are important to represent patients in a way that helps support and assist medical decision making. The kind of approach we have here, and this is quite an advanced demonstrator that was built, was essentially a service-based framework where we had SOAP services in some cases, HTTP services, grid services. In some cases there are very large-scale cluster-based computing problems here where you have to take images, complex images, and align them through time because the breast is an elastic structure. Over time a cancer may be growing and changing, the breast structure itself may be changing. How do you align those things so that you can understand whether there's been real change in the shape is a challenge. And so the kind of services we're talking about here are image analysis, looking for problems in images, classification of those potentially problematic areas that have been identified, regions of interest, the patient data themselves, their medical history, very routine services. Many cases medical practitioners in this area find it very difficult just to systematically write notes up of the consultations between the specialists themselves. And again, the reason I show this is that fundamentally the approach we took here was to have an underlying representation of the patient and the actual test results and the content associated with the various diagnostic stages represented in an RDF format using, in this case, a variety of ontologies that were being mapped into one another. And this actually gave rise to a very nice initial system. This is not a system for clinical deployment, but it shows how we were hooking information together. So an ontology on the left there is just simply showing that a whole range of patient data was being hooked together. Interesting example here of the Semantic Web challenge was that in the UK, the privacy laws on getting hold of any patient data for research use are very, very stringent indeed. In fact, almost all our patient use data was from the US, where your entitlements to reuse content are much more in advance of ours, certainly.
You mentioned, do you have any studies or insights as to how these user interfaces are used as lenses on with data?
This interface is very much from the research development point of view. I can't say that we've done a huge amount in this project on that. I will talk to a project a little later where we've worked very hard on the user specification. All I will say is that here we've got a timeline view of a patient where we're trying to thread their medical records together and all of the associated information that patient's had derived from them. So here we can see that this patient's had an actual mammogram taken on a particular time, and here's actually an example of one of our services. This service is invoked from Sheffield, the University of Sheffield, which is a language generation service that takes the various RDF annotations and assembles a brief patient record based on it. So that's kind of an example of a microservice. Now, whether we've visualized it correctly is one thing, but certainly the utility of that service was very highly regarded by the practitioners.
That blob of text
was auto-generated. That was auto-generated, yeah. In fact, if you read it in detail, it's not Shakespearean in construction. It's a little bit repetitive, but it's auto-generated.
See, I mean, I again have a sense for how well that's done. You know, how hard that problem is.
That problem, I mean, again, evaluating these kinds of technologies against real healthcare situations is a challenge in itself, partly because many of the advanced digital scanning methods that we're pulling together here are not routinely deployed in many of the hospitals we're looking at. What we did find when we were working with the two hospitals in particular that were very state-of-the-art in the UK, this was Oxford and one of the London teaching hospitals, was that the information overload and management problem was so acute for many of these clinicians that almost anything that kept it together in one place from different service providers was seen as a huge benefit. Yeah.
There's definitely a chicken and egg thing going on. You imagine if you had a nice set of definitions, you had tools that would do better capture.
Yeah, absolutely true. Yeah. But I mean, we can actually see here the various services being invoked. We actually see here that this particular patient has had a whole range of tests conducted over time. There is actually an MRI mammogram registration tool that actually sends off to a service in London to actually do the overlaying, and then some region identification algorithms that look for suspect lesion areas and so on. So we know there's a lot of work to do in this area on usability and clinical usability. One of the interesting things is that in the UK, the clinicians themselves in this area will have different reporting standards depending on which national health region they're working in. And unified standards are actually a challenge in this area itself. In fact, the ontology engineering that you do to try and clarify areas of common and intended meaning in areas like this are ones that the medical community is importantly concerned with. Let's go back to the philosophy, because actually this application threw up something very interesting to us. When you look in medicine, you clearly see an area in which the meaning of terms are determined partly by people's usage, by institutions, by expected norms. And here's a nice example. This is an example from breast disease. There is a definition here how you identify a certain sort of cell. Indeed, this is a particular common sort of false positive. finding. So something that's worried about when in fact it's benign. And the key to this whole identification is that an appropriate procedure has been gone through, regularized, to actually stain the cells. And if that procedure isn't followed and the norms laid down to follow through that whole process followed, then you can get all sorts of misidentification problems. And indeed, you can actually formalize those processes in quite nice ways. And there are studies to show how if you deviate from the particular staining processes, then you can actually get huge inter-expert variability. That their ability to achieve consensus on diagnostic outcomes is very profoundly affected. All of this is to say that in practice, being able to manage a term as an example of a particular malignant cell type is a complex social process. And unless you understand some of the elements behind that, if you understand that that's a process of rule following, a process of agreements about the utility of that approach, you miss a huge amount of the importance of the way those terms are used in actual medical practice. So you may have built your ontology and you operationalized your information management tool assuming this was on the assumption that this is a stable term. That doesn't mean it's some kind of simple-minded logical atom of meaning. That's the point I really want to make there. Okay. We've gone on to do a lot more work in the project on trying to harvest content from the open web. As you might imagine, in a variety of contexts at the moment, agencies are very interested in detecting patterns and trends across large amounts of open content. I really don't have the time to follow through too far on this now. I'd like to perhaps return to this in the question time. If people are interested, we can perhaps have a look at this. But let me go on to talk a little bit. This is where you change your mind because you think it's so interesting. Let me come back to this. Let me show you an example of the system then. Maybe not because it can't find it. Okay. Here's a system in which essentially we built an ontology. In this area, it was the energy domain and climate data sets. We were interested in understanding what we could intersect off of the open web in a non-classified domain that would show the power of information integration using ontologies. So there's a lot of data out there from various websites, Department of Energy, UN, various commercial sites on energy consumption, data sets on gasoline production, data sets on CO2 emissions and so on. And it's not too hard to then harvest associated documents that relate to these key terms. So here we're actually going to look at an application that mixes dynamic link injection over hundreds of thousands of documents out there on the web with this ontology web approach. So essentially what we've done is harvest a lot of information off of the open web, representing it again as an RDF graph. Here we're looking at crude oil production. There's a lot of data sets here that we're going to visualize now. One of them is crude oil production in barrels. We're going to pick a particular country, it's Iran, and over time, those three countries, Iran, Iraq and Kuwait, we can see that the production curve, rather unsurprisingly, shows some dramatic events around about, in this case 1990. That example there was where we were able to take the harvested content off of the data energy sets and look for associated threads off of the various news wires that we're looking at to explain what was happening in that context. So the ontology has given us a context in which we can go looking for other content on the web. So the context is oil production, it's a geographical region, and you can then précis that kind of information over a time period. That's a nice example of where you can get this integration of information types. Similarly, if we look at CO2 emissions, we're looking at I think that's the CO2 emissions of the United States, the United Kingdom, manfully trying to follow our protocols under the Kyoto Accords. And here actually we're looking at documents that have been harvested off of the web that make mention of the key terms we're currently focusing on in our ontology, and indeed marking up the websites according to the ontological terms that we're interested in. So here we've actually got a variety of stories, quite common stories of various threats to wildlife posed by global warming. There's actually a story we found, this is the BBC website, where we used these link injection techniques over large document sets and found a story in 1999 of polar bears starving as the Arctic ice cap melts. They had an exactly self-same story that was published in 2000, but they'd actually lost the link on their own website to the earlier story. And this is one of the interesting examples with the sheer amount of content out there that some of the threading can be lost.
Actually, if you go look in the AP Newswire, there's certain file stories that they run whenever the staff's on vacation.
Right.
Okay. And you know that it's a slow news day when you see these file stories running on the wire.
Right.
And they're rather predictable. They tend to run on weekends when it's good weather in the summer.
Yeah, that's right. Okay, maybe there's a lot more we could find in the surrounding context to kind of predict these things then. Yeah.
How did you formulate the query that went out and found that bit of free text now?
The free text.
This 19 event.
Yeah, the free text was being harvested because earlier on you saw an ontology description of the areas of interest, and it had to do in this case with CO2 emissions. It would have had to have done with an epoch of time. That's being set earlier on by your navigating the ontology. Essentially, that's what you're doing. So you're using that
query was launched to find
that query there. Actually, we could see it earlier. We can have a look back into that. It would have been some keyword terms that would come from the ontology. So CO2, it would have had to do with a period of time, as I was saying. It would have had also to do with natural impact, natural environmental impact. So it would have been an intersection of probably on the order of 4 or so key search terms there. And that would have got a document set down that would have been on the order of a few hundreds or thousands of documents, and then actually you actually rank them by relevance and would have threaded through them. So I showed you the kind of final story there rather than a bit more filtering that you would have had to have done. Yeah. But it gets sorry.
The search engine for doing that latter part of it?
Yes, you do. Yes, in fact, we don't do any better than the kind of out-of-the-box statistically based search engines. Once we've got that degree of focus down, yeah.
So what you're doing basically is figuring out which terms to stick into the web search engine to...
We're setting the context more strongly than that because we're also enumerating, if you like, the universe of interest as well in terms of the total document sets that we're looking to pull down and look at and index. Yeah. So this would be a tool that you would look to run in some sense over sectors or areas. It wouldn't be indexing routinely the whole open web in that sense. Yeah. Okay. I've got about another 5 or 10 minutes here. Let me give you a little bit more of a sense of the other work we do in this area. Because the semantic web, in the way that we're interpreting it, is all about networks of relationships expressed between objects, usually expressed as RDF graphs. One of the obvious points about this, once you've represented your content in this way, is you can do various forms of network analysis. And indeed, the whole area of social network analysis is an interesting one. It has a lot of interest from communities such as the friend of a friend community, and intelligence communities are looking to kind of try and detect patterns of relationships between objects in either blogs or published literatures and so on. And indeed for ourselves, I mean, just to show you again, this is a tool that we have found useful, and it speaks to the fact that actually a lot of the examples I've shown you today, some of them have this relationship back to our own research community, that as a research community of scientists and engineers, we have our own problems of understanding the patterns of interaction and the information at our disposal. This tool is simply a tool that allows me to examine my own community of practice, and this would be the objects of, if you remember under the computer science view of the UK, it showed me which individuals I was most closely associated with. And this is a community of interest perspective on me from 1990 to about 1995. So that 5-year period, it's showing individuals and projects and work that I was associated with at that point. It's picked this up off of the variety of information that's been harvested on me from the project databases, from the various other semi-structured sources. And I should say that a lot of our semantic web applications depend, crucially, on structured database sources to act as a strong nucleus for the information integration. This is not just running on the unstructured open web. And actually, as we change the kind of time slot, looking from 2000 to 2005, we can actually see the topology of my relationships and interests markedly changing. And in fact, over time, my world condenses down into Wendy Hall, my colleague here, people like Nick Jennings, who works in agent-based computing. That set of relationships has very dramatically changed, and being able to track the evolution of your interactions over time starts to suggest an interesting new class of tools for understanding a whole range of patterns. Now, the research communities themselves are, I think, a natural place to begin to look, and it speaks to an interest that we might think of as asking ourselves questions in research of who's doing what where with what impact. Stephen Harnad, a colleague, has called this moving towards the open research web, so that a set of services which rather automatically do the citation counting, do the impact analysis, look for the communities of interest, look where the hubs and authorities are in fields. And I think as we begin to get to a stage where more of our content might be equipped with explicit descriptions of micro-ontologies that describe research areas of interest, areas of funding, the kinds of examples I've shown you, this opportunity becomes very real. Okay, some reflections. Just to wrap up, I think in the semantic web, as Eric was pointing out before this talk, something of a loaded term. People have seen various articulations of it and come to think of it as some kind of repurposed good old-fashioned AI hype. And certainly there are times, and there have been moments when that sounded very much the case. But what I would try and argue for here is that there is a way of seeing elements of the enterprise which are really about releasing the potential for reuse, serendipitous reuse of content in particular. So two elements to focus on. One are the services, the integration of services of the sort I've been showing in some of the examples, through semantic annotation, through simple descriptions about capabilities, and an enrichment of the potential meaning of content so that it can be picked up by other potential users. And you're starting to see this, I think, in any event, in the varieties of mashups you now see with people like, with the interesting Google Maps overlaying all sorts of other services on top. Informally, this process is happening. And the question is, if one were to perhaps have resources which were more explicitly semantically annotated, would this happen at an even larger scale? We have also been keen in our work to promote real application exemplars of the semantic web. So this was work that was done at Southampton with the Department of Engineering in the whole area of design optimization, where we're trying to work out how to bring information together to solve very hard optimization problems in engine design. I don't have time to go into that in any detail now, but it's important that, and for people of interest, it's important to know that these real application examples exist. And here, the use of semantics is to thread processes and services together and to organize workflow. In another application, and actually the reason I put this one up is that it's, of all the applications, it is one that uses Microsoft infrastructure. In this area, we were looking at bringing information together. It's a military context, trying to understand how we can integrate information from both the open and controlled web to describe situations as they unfold in military contexts. And the kind of technologies we're drawing down on here include a variety of well-understood components, NASA's geographic visualization software, .NET applications, a semantic web API, in fact, that we built using .NET. And this essentially allows us, again, to begin to take a variety of information resources and thread them together. The UK is a particular interest at the moment in various parts of Afghanistan because it's deployed troops there just recently to look after the southern Helmand province. And here the idea is, can we begin to thread together to provide an overview of situations unfolding, sources of information that come from RSS feeds, from news feeds, from the military's own information sets and so on. And we actually think that this promises a really rather interesting new way of information integration. Network-enabled capability that the military talk about has many of the same characteristics as network-enabled health. It's about service integration and information fusion. So we're also involved, both Wendy and I actually, in trying to commercialize some of this technology in a way that that provides not just B2B or enterprise opportunities, but consumer-facing propositions. So here we're actually just announced a company in the UK which is trying to use semantic web technology to provide some degree of control over an individual's personal information in the digital world. Now, this is not privacy-enhancing technology. It's about trying to understand what is out there about you, such that you can then begin to do something about that should you wish to, either to promote yourself or have various forms of restitution. In the UK, there are lots of situations where there is legal entitlement to have inappropriate information removed or freedom of information requests made. Very, very little of it is taken up by the average citizen. It's difficult to enact. People aren't sure what's out there about them. And we're kind of imagining a model in which we begin to do some serious harvesting against the kind of ontology reference models, both in structured data sets and the unstructured web, to try and provide individuals with some characterization of their digital persona. This is a company that's received substantial VC funding at this point, and has made a commercial announcement. Its beta technology is beta technology is about to become available in about a month, and there'll be a commercial launch to the UK population in September, late September this year. So we hope that'll make some progress.
Real risk that this very same technology might be misused?
That's a very good question. Of course, it's this company's business is to support information management for the individual. So this is not about taking that data and reselling it, or about giving it to other companies to do with as they will. This proposition will be very much now the individual taking control.
Procedures are very good.
Well, but of course the problem is that if you actually engaged on this large scale, and it is one of the issues I think that's thrown up by semantic integration projects, is that what is the intersection of all the information out there likely to indicate about you? I mean, we know from all of the work in identity theft that it gets easier and easier as people become smarter about trying to find out your mother's maiden name, your date of birth, your postcode. You need about 4 or 5 key questions in the UK to take out a mobile phone. So there are real issues, and I think this company is very much in the space of trying to be a consumer-based champion. Now that is hoping that the consumer has, certainly the consumer has, there are real conversations that consumers have in this space that is a worry about precisely these issues. Okay. The other area where we see a lot of opportunity is in the public sector. There is a directive in the European Union that means this is national law now, that any information gathered on the individual citizen by a government should be made available on free and fair terms to the citizenry. Now, that is all about trying to make people aware of a whole range of data, the meteorological office, planning regulations, you name it. The government collects a huge amount of information, and the public sector information office is now trying to understand how it can begin to connect that information together and provide services to individuals. And again, this semantically mediated framework is one they are quite strongly supportive and attracted to. And we actually have a project with the Cabinet Office, which is the Prime Minister's office in the UK, to investigate the technology in that area. So I do believe that there are a number of significant drivers for change that are, in their different ways, going to accelerate elements of a semantic agenda. I think the nature of research and publication, the fact that there's more of your research papers published digitally, there's more information about you as an individual, your research interests, start to suggest that there are tools there. And you can see these in the medical domain. PubMed Central and other services that provide really rather sophisticated methods for tracking between papers and literatures. One can begin to do that. In the e-science community, there is now an increasing interest in publishing the core data in the journal papers as well as the text around it, and the conditions under which the data was collected, the experimental initial conditions. Again, that is work where, and there are good examples of this, I think, where communities are saying, you know, what sorts of metadata, provenance data do we need to associate with our chemical structures as we generate them, so that we can better understand the conditions under which an experimental result could be reproduced, for example. The abundance and ubiquity of data is driving us this way. The whole notion of the information value cycle. A geopolitical context in which people are increasingly concerned about knowing as much as they can, or indeed maintaining a degree of privacy, this kind of information challenge. And there is significant regulatory and legislative developments. They vary from country to country, that are pulling on the one hand to make information available and worrying on the other about the use of personal information. And as a segue to what Wendy will be talking about this afternoon, lessons learned. Content is primary, that the ontologies as lightweight mediators are effective. There's already the standards in place to do significant work here. Much of what we do has a socio-technical element to it. It's about people and the conventions that they follow. There are some very hard problems at the heart of our subject, and we refer to this agenda as a web science agenda. How do you really understand the scale properties of these systems, how to do reference, co-resolution, all those examples of you out there in various forms, how they collapse down to the same individual, or different individuals if you so want them to be represented. There's a whole issue of push versus pull. Can we start to move to an environment where the instinct is to publish your data more richly described? A scientist from the Met Office I was talking to the other day made a very interesting observation. He says, here in the Weather Bureau of the UK, we provide a lot of content passively. You can FTP lots of climate data. It's there. What we don't do is provide that content actively. We don't think hard about ways that would make it much clearer about what those actual fields mean, what the relationships are, what the context of collection of the numerical data or the statistical data being represented is. And that, I think, is an important, one of the important evangelical missions for a web of data that could really move us into new opportunities. Fidelity, of course, there's a whole issues. I haven't talked a lot today, but there are big issues around the whole notion of trust and provenance for the content you're going to aggregate, its various quality attributes. And then how we intercept what we might think of as a social software movement. There's a lot of interest, of course, in large-scale annotation efforts, whether that's things like Flickr, where large numbers of people start to mark up photographic collections. The interesting thing about those annotations is that as more people do it, you start to get key categories emerging across their various markups. And the interesting question is what relationship there is between these statistically emergent categories and these more formal ontologies we talk about.
The tags are very coarse-grained.
Yeah, I think that's exactly right. And indeed, they're tags. And the question there is, what can you do with a landscape which roughly divides up in quite a stable way to these top-level categories? Can you do anything at all of interest? I think that's a question. And I'll finish with a really kind of both Wendy and I kind of regard as important work underway for us, which is to try and take a lot of the issues raised in today's talk and understand them from a more fundamental position, what we think of as a web science agenda. And indeed, we're working with Tim Berners-Lee and his group at MIT to try and articulate an agenda of the really hard problems at the heart of computer science that we think this kind of web of data is going to express and articulate. So with that, I'm actually not going to rush through the manifesto. Wendy will talk about that a little this afternoon. What I will do is just indicate that there are a bunch of resources here that give much more detail, both in terms of publications and some of the demonstrations of the technology and approach I've talked about here today. And thank you very much. Thank you.